Hello, and welcome to this online training on Intel Nios V processors booting. Feel free to pause, move forward, or go back as you need during this presentation. At the top right of the presentation, you will find a list of helpful links and resources on the subject. Let's get started. The Intel FPGA portfolio supports this transformation, including discrete and integrated FPGAs that are expected to improve processing efficiency, task specificity, and connectivity. Intel FPGAs can provide a variety of workloads in network processing as well as compute and storage acceleration. FPGAs are mass-produced, standard product ICs that can be reconfigured in the field to accelerate virtually any digital algorithm. They offer greater throughput, execution speed, and energy efficiency than CPUs on computationally intensive parts of algorithms, but with the ability to adapt quickly to changes in algorithms, data patterns, or performance needs. They can be reconfigured in the field to accelerate virtually any digital algorithm. They are available in 5 current families: Max, Cyclone, Aria, Stratix, and the newest family Agilex, all with increasing capacity, performance, and feature sets. The objectives for this course are to describe the different booting methods for Nios V processors and understand the hardware abstraction layer and linking applications roles in the boot flow. You can configure the Nios V processor to boot and execute software from different memory locations which are execute in place and copied to RAM using boot copier. The boot memory can be the quad serial peripheral interface flash, on-chip memory, or tightly coupled memory. The Nios V processor embedded programs development is based on the hardware abstraction layer, HAL. The HAL provides a small bootloader program, also known as boot copier, that copies relevant linker sections configured in the BSP editor from the boot memory to their runtime location at boot time. The services provided by HAL are device drivers, which provide access to each device in the system. The HAL API provides a consistent, standard interface to HAL services, such as device access, interrupt handling, and alarm facilities. System initialization performs initialization tasks for the processor and the runtime environment before main. Device initialization instantiates and initializes each device in the system before main runs. The hardware abstraction layer, HAL, is a lightweight embedded runtime environment that provides a simple device driver interface. By design, the hardware abstraction layer attempts to enable as many services as possible based on the peripherals present in the system hardware, provides control over initialization process, system optimization and configuration. The changes made to the hardware configuration propagate to the HAL device configuration to avoid any inconsistencies in the IP. After you have created the custom component, configured everything in the parameters for Nios V, and added the components and connections necessary, you can now use the BSP editor and generate your board support package. The board support package, BSP, provides a software runtime environment customized for one processor in a Nios V processor hardware system. A BSP contains the following elements: hardware abstraction layer, device drivers, optional software packages, optional real-time operating system. Board support package editor is provided inside Platform Designer to allow configuration and generation. After the BSP project is generated from the BSP editor inside Intel Quartus Prime software, 2 files are produced. Linker.x, the linker command file that the generated application's makefile uses to create the .elf binary file. Linker.h contains information about the linker memory layout. Typically, the linker section allocation scheme works during the software development process because the application is guaranteed to function with the correct memory settings. During BSP configuration, the tools perform the following steps automatically. 1. Assign memory region names. Assign a name to each system memory device and add each name to the linker file as a memory region. 2. Find largest memory. Identify the largest read and write memory region in the linker file. 3. Assign linker sections. Place the default linker sections, text, row data, RW data, .bss, heap, and stack, in the memory region identified in the previous step. 4. Write files. Write the linker, X and linker, H files. Typically, the linker section allocation scheme works during the software development process because the application is guaranteed to function if the memory is large enough. To adjust the settings for the linker files produced from the BSP generation, go to the Linker Script tab in the editor. The configuration in the BSP editor has two main functions. Ensures that the processor software is linked in accordance with the linker settings of the BSP editor and determines where the software resides in memory. Positions the processor's code region in the memory component according to the assigned memory components. You can modify the linker script using the following methods only. Add a memory region. Maps a memory region name to a physical memory device. Add a section mapping. Maps a section name to a memory region. The BSP editor allows you to view the memory map before and after making changes. This script ensures that the processor software is linked in accordance with the linker settings of the BSP editor and determines where the software resides in memory. The linker script also positions the processor's code region in the memory component according to the assigned memory components. This is the flow described for Nios V processors booting. Starting from reset, the processor jumps to the vector specified as the boot code start. Then the application code is copied depending on the boot options. The boot code initializes the processor. Then, depending on the configuration of the code, it may copy the initial values for data code to another memory space specified through Alt_load configuration. Then the boot code starts the application code and data memory space. The boot code then initializes all system peripherals with the HAL drivers. Finally, you can enter to main. The methods in the table are the supported boot memories for configuration with QSPI. First, we will talk about the execute in place from boot flash method. When the Nios V processor application executes in place from boot flash, the BSP editor performs the following functions. Sets the text linker sections to the boot flash memory region. Sets the .bss, row data, RW data, stack and heap linker sections to the RAM memory region. You must enable the Alt_load function in the BSP settings to copy the data sections, row data, RW data, exceptions, to the RAM upon system reset. The code section, text, remains in the boot flash memory region. Control block-based devices refer to the Intel Cyclone 10 GX and Intel Aria 10 devices. SDM-based devices refer to the Intel Stratix 10 and Intel Agilex devices. This is the configuration for the first booting method using configuration from QSPI Flash. When Enable Alt_load functionality is used, it acts as a mini boot copier and as a copier for data sections, row data, RW data, exceptions, to RAM. The text section remains in the read-only section in the booting flash memory region. This partitioning helps to minimize the RAM usage. You can see that there are different BSP editor settings available. For example, Enable Alt_load option. This allows the function in the HAL to be used and the setting is HAL. Linker. Enable Alt_load. This will copy the sections. If you want to know more about the other available BSP editor settings like Alt_load copies to sections of the RAM, you can go to the Nios V processor configuration and booting solutions sections of the Embedded Processor Design Handbook link provided in the resources sections. In this booting method, Alt_load function is activated as the boot copier. Retaining the read-only section in configuration QSPI minimizes RAM usage but may limit the code execution performance. This is a great option for when there is only a limited on-chip memory available. The Nios V processor application is programmed into the configuration QSPI flash. The Nios V processor reset agent points to the configuration QSPI flash to allow code execution after the system resets. The GSFI bootloader is the Nios V processor boot copier that supports QSPI flash memory in control block-based devices. The boot image is located right after the boot copier. The Nios V processor reset offset needs to point to the start of the boot copier. You can add the generic serial flash interface Intel FPGA IP from the IP catalog in Platform Designer. We will now take a look at how you can boot from QSPI using GSFI bootloader. This is the second option of the booting method. At the start of the memory map is the FPGA image followed by your data, which consists of boot copier and application code. Once the project in Intel Quartus Prime software is compiled, the exact size of the FPGA image will be determined. Reset vector offset needs to be set in Platform Designer accordingly in the parameters for Nios V. You can use a boot copier to copy the Nios V processor application from the configuration QSPI flash to RAM when you require multiple iterations of the application software development and high system performance. For this boot option, the Nios V processor starts executing the boot copier software upon system reset, which copies the application from the configuration QSPI to the internal or external RAM as seen in the diagram. This is the description for the last type of device that uses SDM as a bootloader. The SDM bootloader is a HAL application code that uses the mailbox client Intel FPGA IP HAL driver for processor booting. Upon system reset, the Nios V processor first boots the SDM bootloader from a tiny on-chip memory and executes the SDM bootloader to communicate with the configuration QSPI flash using the mailbox client IP. Then the control is transferred to the user application. On the right you can find that the Nios V processor runs bootloader from on-chip memory. Then the SDM communicates with flash. The copies are reproduced to RAM in step 3. Notice it can be on-chip RAM and external RAM. Then it changes to software in RAM on step number 4. The application binary .hex file is loaded into the on-chip RAM when the FPGA is configured, after the hardware design is compiled in the Intel Quartus Prime software. Once the Nios V processor resets, the application begins executing and branches to the entry point. Execute in place from on-chip RAM does not require boot copier because Nios V processor application is already in place at system reset. The use of the Alt_load function is recommended for this booting method so that the embedded software behaves identically when reset without reconfiguring the FPGA device image. The on-chip memory is initialized during FPGA configuration with data from a Nios V processor application image. This data is built into the FPGA configuration bitstream. This process eliminates the need for a boot copier, as the Nios V processor application is already in place at system reset. When working with this project in Platform Designer, make sure that the memory is in the system design. Execute in place from TCM does not require boot copier because Nios V processor application is already in place at system reset. Once the Nios V processor resets, the application begins executing and branches to the entry point. The tightly coupled memories are initialized during FPGA configuration with data from a Nios V processor application image. This data is built into the FPGA configuration bitstream. You can configure the TCM instruction and data settings in the Nios V IP parameters window inside Platform Designer. This provides a quick summary of the booting methods and the differences between execute in place and booting using a boot copier to RAM. The tools and settings for each one of the booting options are described in the following tables. This table describes the boot options from QSPI Flash and QSPI to RAM with GSFI bootloader. Both options need configuration in the Nios V IP parameters window inside Platform Designer to set the reset agent as configuration QSPI. Then for the BSP editor settings inside the Advanced HAL section, you can configure and enable the options for the booting method. Inside the BSP editor, you can also set the linker sections in the BSP linker script tab such as text, exception, or RW data to on-chip RAM or external RAM. The connections for the Nios V project in Platform Designer require the GSFI IP added to the design and signals connected. For devices using SDM bootloader, the reset agent needs to be set up in the Nios V parameters as bootloader ROM. The adjustments needed for the BSP editor settings in the advanced section for HAL linker can be done to enable alt_load functions such as enable alt_load copy row data, among others suggested in the table. The linker script sections need to be set as indicated in the table for bootloader ROM. The needed connections for this design require for memory and mailbox IP to be added to the system view. These two execute-in-place boot options require the BSP editor settings in the advanced section for HAL linker and for the linker sections to be modified according to the suggested settings which enable allow code at reset function and the linker sections that correspond to each option. You can learn more about each booting method and options in the Nios V processor configuration and booting solutions section of the Nios V Embedded Processor Design Handbook link provided in the resources section of this course. You can find examples to get started with Nios V processors design through the Design Store link provided in the resource section, or in our rocketboards.org website for examples with Nios V processors for Intel FPGAs. You can also find examples in the Design Store. It will lead to different resources, or you can go to the Intel FPGA Support Resources website and target your development kit. You can also open examples from inside Intel Quartus Prime software to get started with tested designs. You can find them in the main window. You can find more information on the resources available in the section for this presentation at the top right, or you can go to intel.com and search for Nios V processor landing page, and take a look at the resources, quick videos and tutorials to get started. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel, which contains 5 minutes quick videos along with longer, more in-depth training videos. There is the Intel FPGA training website, where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses with labs and demos. Lastly, you can also enroll in a live, instructor-led course presented either in person at an office local to you or virtually over the web. All instructor-led courses have hands-on labs exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages, called landing pages, dedicated to specific FPGA technology like in high-speed interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA applications engineers. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email fpgatraining@intel.com with any of your thoughts or comments. This concludes the training. Thank you and have a good day.